Hello guys, this is Mohammed Furquan from Engineering Physics Department. I got an A grade in PYL101 and today I will be teaching you postulates of quantum mechanics. For that, we are first going to study some basic terminologies that will be used. First, we need to understand the concept of observables. Observables are physical quantities that can be measured. They are also known as measurables. Examples of observables would be position of a particle, momentum of a particle, angular momentum, it may be spin of a particle, etc. Okay. Second, we need to understand the state of a system. So, in science in general, we try to characterize the state of a system using these observables. So, if we have a particle in 2D space at some position with moving with some velocity 2 meter per second in this direction maybe, then this is one possible state of this 2D particle. Okay, so this is one possible state. Similarly, we can generalize this concept to a state which is characterized by, let's say, n observables. So if we have n observables for a state O1, O2, O3 up till On, and measurement of these observables will tell you the state of the system. For example, if we have a general observable OK, then the measurements of OK may be lambda 1k, lambda 2k up till lambda rk. Then what we are trying to say is that we will collect these measurements. For example, OK may give measurement this, O3 may give some this type of measurement, O2 may give this type of measurement. We will collect all these measurements. We will collect all this set of all these lambdas, and that set will tell us the exact state of the system. For simplicity, let's take a system with two observables. Suppose we have a particle on the number line and we can measure its position at a certain time and its momentum also. Suppose it has position x and momentum p. Then these two quantities, if we are able to tell these two quantities, then we are able to tell the exact state of the system. Okay. Now we need to understand that how we are going to represent this state in terms of the vector notation that is being used in quantum mechanics. For that, we introduce concept of Ket spaces. So to represent a state in quantum mechanics, we use this Ket vector notation. This psi represents the state of a quantum system. This represents the state of a quantum system, and it is a column vector. For example, if we have a system of a single particle which is moving on the number line with some at some position x with momentum p, then we can denote the state of system using this notation. Okay. It may be possible that there are infinite states. For example, in the case of the particle on a single line, we can see that there are infinite possible values of x and p. So there are infinite states possible. So, but that is no problem in quantum mechanics. Uh, if there are infinite values of x and p, then the basis that is made by the vectors that we are going to get from various values of psi will have infinite dimension. Okay. And we have certain set of vectors, certain kind of vector spaces that deal with these type of dimensions, and we call them Hilbert spaces. Hilbert spaces, they can deal with these infinite dimensions. So till now we have concluded that a quantum system is denoted by a state psi which belongs to the Hilbert space H, and it is characterized by certain observables in the system. Now we need to understand the concept of operators. So in linear algebra, operators are something that act on, so suppose if we have an operator A, then this operator acts on a vector V to give another vector V dash. Okay. So an operator acts on the vectors of a vector space V to give you vectors of a vector space W. But in quantum mechanics, we are concerned about linear operators. Linear operators are something that act on a vector space, that act on the vectors of a vector space V to give you the vectors in the same space only. They also have some properties that we call the properties of linearity. For example, if an operator A acts on these two vectors v1 and v2 from vector space V, then this can be written as v1 plus beta A v2. This we know as property of linearity. Okay, so we are going to deal with linear operators, and in these linear operators we are mainly concerned about the Hermitian operators. The reason we are dealing with linear operators is because a linear operator can be represented as a square matrix of dimensions n by n. So we can represent a linear operator using a square matrix, and we are mainly concerned about Hermitian operators. So Hermitian operators are those operators. An operator A is Hermitian operator if the conjugate transpose, which is also known as the Hermitian conjugate of A, is same as A. So I am going to explain this by an example. Suppose we have an operator A, which is denoted in the matrix notation as this iota O minus iota 0. Okay. Then the Hermitian conjugate will be evaluated as, first we will take the transpose of this operator. So using the when we take the transpose of this, we get the same result, and when we take conjugate of this, then we are going to get this, which is equal to minus a. This means that A is not Hermitian. In fact, it is anti-Hermitian because conjugate transpose of A is minus A. So this is an anti-Hermitian operator. If we take identity operator, then the conjugate transpose of this will be same as I, which means that I is an Hermitian operator. And the reason we are concerned about Hermitian operators is because the Hermitian operators have some special properties associated with themselves. Hermitian operators, for example, Hermitian operators have real eigenvalues. We will see why these properties are valuable when we finally understand the postulates of quantum mechanics. Okay, so this is all about the basic terminologies. Now we are going to get through the postulates. So let's understand the postulates of the quantum mechanics. I'm going to introduce only the time independent postulates. There is one postulate also that relates the that evaluates some operators that can tell you the evolution of a certain state of a system in quantum mechanics, but I'm not going to cover that. Okay, so I'm going to tell you the postulates of time independent quantum mechanics. So for that, we have first postulate as that the measurable quantities that is the measurables in quantum mechanics are denoted by linear operators. Okay, so we have a linear operator for each observable. We have for position, we have position operator as position operator for position. We have momentum operator for momentum. We have angular momentum operator. We have spin operators, etc. The second postulate is about the measurement of these measurables. So the second postulate states that to measure the state of a system, we need to measure all the observables, and to measure those observables, we need to find eigenvalues of operators corresponding to some measurable. That is, the eigenvalues of an observable will give you all possible measurements of the observable. Suppose we have an operator A, which basically which is basically the operator corresponding to the observable A. So when we are calculating this lambda I eigenvalue corresponding to some eigenstate, this is an eigenstate of a system. Eigenstate basically means the state of a system which satisfies this equation. And this equation basically means that when the state is acted upon by an operator A, then it gives you a a scalar multiplication of that state only. That state is known as eigenstate, and corresponding to each eigenstate we have certain eigenvalues. So what does this postulate tell us? The postulate tells us that this lambda I is the measurement of observable A when measured in state psi I. So this is our second postulate. The third postulate tells us that unambiguously differentiable states are represented by orthogonal vectors. Represented by orthogonal vectors. So what does this mean? That unambiguously differentiable states are represented by orthogonal vectors. So what we mean by unambiguously differentiable states is that these type of states cannot be differentiated by any measurement of an observable. Okay, so if we have two states, psi I equals O1, O2, On. This is our one particular state, and the second state is this. Okay, and these two set of observables these set of observables are yielding the same measurement. Then we say that the states psi 1 and psi 2 are same. But if they don't, then we say that the states are unambiguously differentiable. And if they are unambiguously differentiable, then the states will be orthogonal, which means that psi 1, psi 2, the inner product of these states will be 0. Okay. Then moving on to the last postulate. The last postulate states that if psi is a state vector of a system and it is characterized by an observable A, corresponding to which we are getting eigenvalues as lambda 1, lambda 2 up till lambda n, then probability that the measurement will yield the value as lambda I is given as psi ai and ai psi, where ai represents the state eigenstate vector corresponding to eigenvalue lambda I. That is, when A is acted upon this AI vector, then it will give us lambda I AI. So this is all about the postulates. So for review, let's move. Let's try to summarize what we have learned. We learned about observables, which are physical quantities which can be measured. Then we got to know how we characterize a state of system by using n observables. Then we got to know about Ket spaces, which are column vectors that are used to represent states in quantum mechanics. Then we learned how to deal with infinite states of a system using Hilbert spaces. Then we learned about operators, especially linear and Hermitian operators. Okay, and then we learned about the postulates, the postulate that states that the measurable or quantities are denoted by linear operators. Then we have eigenvalues as measurements of these measurables. And then we have unambiguously differentiable states represented by orthogonal vectors. And then we got to know about the probability of finding some particular eigenstate. Thank you so much.